We're to our third and final example of calculating expected values. And the subject of this example is going to be gambling. This is the big one. This is where very, very subtle gaming techniques can be used to cheat people out of money. All right, let's see how this works. Let's just do a very simple example. You have a certain game. A person wins $5 if she rolls doubles, but wins nothing if she rolls anything that's not a double. So the question is, for a game to be fair, how much should she pay to play the game? In other words, how much should the person giving the game charge a person to play the game for the game to be fair? Now, to be fair, basically what we're saying is there's a 50% chance of someone winning, 50% chance of someone losing, okay? 50-50 chance either way. And the way that that's indicated in mathematics in the expected value world is that the expected value is going to be 0. Sometimes they win money, sometimes they lose money, and if they keep playing for a long time, then on average, the net winnings is going to be 0. Okay, that's the expected value. So that would be, there we go, that's the setup for the example. So what's the probability of rolling doubles? Well, remember that there are 36 different ways that you can roll 2 dice. And we can easily set up a table to show that. 36 different ways. How many of those ways will roll doubles? Well, you can have 2 1s, you can have 2 2s, you can have 2 3s, 2 4s, 2 5s, and 2 6s. That's 6 different ways that you can roll doubles. So 6 out of the 36 rolls are doubles. That reduces to 1/6. So the player has a 1/6 chance of winning $5. All right, let's put together our table. We don't know how much the person is playing for the game, but we do know that if they win, they're going to get $5 minus whatever they pay. We'll just call that X for now. But if they lose, then they're just going to lose whatever they paid to play the game. What's the probability of winning? Well, we just saw that. The probability of rolling doubles is 1/6. What's the probability of losing? That would be 5/6. Now let's calculate the expected value. The expected value, which we're going to say is 0 because we want this to be a fair game, then the winnings, 5 minus X, times its probability is 1/6. Plus the losses, negative X, times its probability of 5/6. We can just go through, do this math, multiply both sides by 6. It gets rid of the sixths in there. And we end up with 5 minus X minus 5X, or 6X equals 5. If we divide by 6 again, then we get that X is equal to 5/6, which comes out to be 83 cents. So if the person running the game charges any player 83 cents to play the game, then on average, the person running the game would not gain any money. They would not lose any money. The people playing the game would not win or lose any money. It would be a fair game, no wins or losses. So what if the person running the game wants to earn some money? Well, that's a pretty simple one. Just increase the price just a little bit. Not much, but just a little bit. So if we instead make the cost $1, then the expected value will be the winnings, $5 minus the $1 they had to pay to play, times the probability of 1/6, plus the losses, $1, times its probability of 5/6. Run that through, and you end up having an expected or average loss of 67 cents per game. Excuse me, not 67 cents. This should be 16.7 cents. So I'm missing a couple of points in there. 16.7 cents is what that should be. So on average, the person running the game should earn 16.66667 cents a game. All right? It's very subtle. Just a tiny little change. A difference of 17 cents. But if you get 100 people to play this, then the person running the game on average would win about $17, $16.67. Okay? On average, that's how much the person running the game would win for 100 games. So, yeah, very, very subtle. Just a small increase in the price, and that changes the expected earnings and shifts it from the player's advantage to the casino's advantage. And we saw an example a while ago about lottery when we were talking about not binomial distributions. We were talking about combinations back in lesson 11. Very dumb way, because you have a very, very low probability of winning and an extremely high probability of losing. And that really shifts things to the casino's side of things. So of all the gambling games out there, lottery is probably one of the worst, if not the worst. So anyway, there's another good example of how to do expected value. In this case, using an example of gambling, and how easily it can be shifted out of the player's favor.